We learned about wave characteristics in the last lecture. In this lecture, we're going to learn about the speed of waves. And there's actually a very important equation, which we call the universal wave equation, and universal meaning that it works for all waves. This slide says when a wave is generated in a spring or a rope, the wave travels one wavelength along the rope in the time required for one complete vibration of the source. So that time is the period. Since speed is distance over time, we can say that the velocity is the wavelength over the period, and because the period is the reciprocal of the frequency, we can also write this as v equals frequency times lambda. That's the universal wave equation. It's a pretty simple equation, all based off of v equals d over t. And this works for all types of waves. Transverse, longitudinal, rotational, visible, invisible, audible, inaudible, electromagnetic waves, mechanical waves. It's the same equation that's used. This is an important slide to copy down. The universal wave equation. This works when your frequency is in hertz and your speed is in meters per second, and your wavelength has to be in meters, of course. On this slide here, you're asked to rearrange the equation in a number of different ways. It's a pretty simple equation to rearrange, so you can kind of look at that there and try that out, but that's basically how that gets rearranged. And we'll do that verbally for these questions because they are pretty short to calculate. This question says the wavelength of a water wave in a ripple tank is 0.080 meters. If the frequency of the wave is 2.5 hertz, what is the speed? So we have 0.080. That is our wavelength, and v equals f times lambda. So this is our lambda. We just have to multiply it by our f, which is 2.5. So we get 0.20 meters per second. That's just the v equals f lambda version of our universal wave equation. This question says the period of a sound wave from a piano is 1.20 times 10 to the negative 3 seconds. If the speed of the wave in air is 3.40 times 10 to the 2 meters per second, what is the wavelength? So here we have the period, not the frequency. So we could think about the wave equation as v equals f lambda, and then we have to change that to v equals lambda over t. We're trying to solve for the lambda, so it's really lambda equals v times t. So in this case, lambda, which is 340, that's our v, lambda equals this v times our t, which is 1.2 times 10 to the power of negative 3. Multiplying those together, we get 0.408 meters. Question 4. The distance between successive crests in a series of water waves is 4 meters. And the crests travel 9 meters in 4.5 seconds. What is the frequency of the wave? So we need to figure out what we don't know in this question. So we have v equals f lambda. That's what we need to use. And we need to rearrange that for f equals v over lambda. But I don't directly have a v, and my lambda isn't directly stated either. What I need to do is figure out from the question, what is my lambda and how do I find my v? So the distance from crest to crest, and successive means the crest next to it, that's also another way of finding our wavelength. So our lambda is equal to 4. And we have here the crest travels 9 meters in 4.5 seconds. Using that, we can calculate our speed of our wave. So 9 meters divided by 4.5 means we're traveling at 2 meters per second. So to find our f, we need to rearrange the equation again. It's going to be v over lambda. So 2 divided by 4 gets us to 0.5 hertz. The transfer of energy using waves is more efficient if the particle vibrations do not absorb much energy. So for example, a more rigid object such as a soccer ball tends to bounce more effectively if it is fully inflated. If it's not inflated, it's going to absorb a lot of energy. Your sound, even if you're speaking, your sound won't travel forever. At some point, the particles in the air are going to absorb a lot of that energy, and they'll stop vibrating or causing the next particle in line to vibrate. So it will eventually, the energy of the wave will be absorbed by the medium. So if the atoms comprising an object are linked by strong intermolecular forces, the wave energy is transmitted more efficiently, and the wave speed is faster. However, if the forces are not as strong, then the energy transmission is less efficient and thus slower. So in the case of gases, you may think that cooler gases are more effective at transmitting sound than warmer gases because they're denser. However, the opposite is true. With an increase in temperature, the molecules move faster and they jostle the neighboring molecules more rapidly. So they, said differently, they don't absorb as much energy when they already have a lot of energy. The speed of a wave along a string, such as a violin or a guitar string, is governed by two properties. The string's linear density determines how much force it takes to make the string vibrate, and the tension of the string determines how well it transmits energy. A loose string absorbs that energy faster than a tight string, which transmits the energy more effectively. These are some wave speed factors that we're going to need to know. So it depends on the properties of the medium, temperature, density, tension. Depends on the molecular forces. If they're very strong, as they are for a solid, we'll have a faster speed. And it depends on the temperature. And with gases, waves travel faster in hotter gases than in colder gases. Earthquakes produce seismic waves which travel through Earth. Primary waves, or P waves, are longitudinal and can travel through both solids and liquids. Secondary waves, or S waves, are transverse and can travel through solids only. When an earthquake occurs, vibrations are recorded at seismological stations around the world. This question here says, if P waves travel 8 kilometers per second and S waves travel about 4.5 kilometers per second, we have to find out how long it'll take to travel to a seismological station that's 2,400 kilometers away. And we want this in minutes. So if this is how far we have to go, and we're traveling at 8 kilometers per second, it would take 300 seconds or 5 minutes. So for the other part, if we have 2,400 kilometers to travel, and we're traveling at 4.5 kilometers per second, this is how many seconds we'll travel, divided by 60. It'll take 8.9 minutes. Last question says, explain how observing P waves and S waves helps geophysicists analyze the structure of Earth's interior. And you can kind of read this here. It says, recall that P waves can move through both solid and liquid materials, but S waves only travel through solid material. As a result, scientists now believe Earth has a liquid outer core because S waves cannot reach regions around the globe that P waves can.